We will resume the program with Filip Ligmajer of Brno University of Technology, who will talk about optically tunable metasurfaces in the visible range. So Filip, the floor is yours.
Okay, thank you. So good morning still to everyone. It's my pleasure to present you the work we have done in this topic of metasurfaces, and it's the stuff I've been dealing with for last 5 or so years. That is incorporation of tunable material, that is vanadium dioxide, into metasurfaces, and by this mean to control and tune their function. So the outline is fairly straightforward. First, I will introduce metasurfaces very briefly, and focus more on their tunability and ways how to achieve this. So this will be some sort of overview. Then I will speak about vanadium dioxide itself, and I will introduce this material. And finally, I will describe the stuff we did with this very interesting material. So metasurfaces, I guess there's no need to introduce them for this audience. These are all very interesting applications of our ability to use nanostructures to control light, and nowadays really interesting applications have been demonstrated, basically fighting with conventional optics and surpassing it in some particular applications. But most of the metasurfaces today are passive, so once you fabricate them, you are unable to change their optical function, and therefore there is this large amount of research which is done towards making the metasurfaces either switchable, that is having this digital control over their properties, or continuously tunable, which is slightly harder, or even freely tunable, which is probably the ultimate goal of these attempts. There are many ways how you can control the optical function of a metasurface. Here is an overview taken from a nice review from Mark Bronkesma's group, and I will now speak about a couple of these approaches in more detail. One, I would say, family of approaches to metasurfaces tunability is use some sort of electrical or electrochemical approaches, or approaches involving liquid crystals, and therefore modulation of the surrounding environment. I consider them as some sort of family of approaches which is somehow interrelated and related with each other. Here is a nice overview of these approaches, where you can use some sort of chemical means or electrochemical means of modulating the optical function, or you can use electrochromic polymers, or, as I said, liquid crystals, to somehow change the environment of the fixed structure or fixed metasurface, and therefore make it tunable or switchable. Another type of approaches is based on mechanical actuation and mechanical means of modulating the optical function. You can either rotate two metasurfaces with respect to each other, and when they are carefully designed, they can introduce again a nice tunability function, or you can use some micro electromechanical system, MEMS system, to tune the metasurface function. There are other approaches based on elastic properties of substrates, and basically elongating, stretching the metasurface on some sort of elastic substrate, and other approaches which all can be somehow put under the hood of the mechanical tunability. Yet another approach is using optics or light to control light behavior, and this can be done either by photocarrier excitation or by some sort of exciting and influencing the metasurfaces using some nonlinear properties of the materials which constitute the metasurface. Here are some nice examples of works from this field. Here is a work from Stefan Meyer, who was speaking here this morning as well, where they use optical nonlinearity for tuning the reflectance of a gallium phosphide nanostructures. So these approaches are also quite interesting and seem to be very promising because of course the speed with which the light propagates and with which you can tune your material. All these processes are really fast. And the last approach which I would like to focus on today is the approach involving phase change materials. There are more phase change materials available, but most of the applications today are based on either of these two. So it's either germanium, antimony, telluride, or vanadium dioxide. Both of them have their pros and their cons. GST, as it is abbreviated, is non-volatile. That means that even after you stop influencing, its properties stay the same. That's the reason why it was used in rewritable CDs, which is something the older audience can know, and maybe younger ones do not. But it has some disadvantages as well. It requires quite high temperatures for switching. It undergoes or suffers from non-negligible volume expansion, and it deteriorates faster compared to VO2, which can be tuned or switched around 68 degrees of Celsius, so quite close to room temperature. It has higher stability and also higher refractive index contrast, so it basically switches more in the optical or infrared range. Its disadvantage is the volatility of this phase transition. So after you stop heating it, it will return back to its room temperature, to its dielectric state, and your optical function will be lost. Although there are some ways how you can somehow mitigate this problem, and I will speak about it later in the talk. So first, let me speak about VO2 in more detail. VO2 is an oxide, and it still seems fascinating to me what is the range of conductivities various oxides can exhibit. So most of you know probably silicon dioxide, glass or silica, MgO, magnesium oxide, and others, which are fairly good insulators. They are transparent and very often used just because of this property. But there are other oxides which have conductivities quite similar to metals actually, and this range is really large. Yeah, this is something like more than 20 orders of magnitude, which is really impressive. And VO2 is interesting because it can undergo a metal to insulator or insulator to metal transition as you go from low temperature to high temperature. Here is probably the first mention of this property, where it's already from late 50s of the last century. And here is reciprocal temperature on the x-axis and conductivity on the y-axis in logarithmic scale. So low temperature is on the right and high temperature is on the left. And as you increase the temperature, there are also other oxides which have similar behavior, but Vo2 is nice because it undergoes this transition around those 70 degrees of Celsius, which is related, or this behavior is related to its structural transition. So Vo2 undergoes transition from monoclinic crystallographic orientation or state into rutile. You see these red dots are vanadium atoms which have this zigzag conformation, and at higher temperatures they just move and align themselves and form the other crystallographic structure. And this subtle motion of atoms and their subtle alignment leads to really large change in the band structure and in the conductivity of the material. And as I said, what's nice about Vo2 is that this metal to insulated transition temperature is one of the closest ones from many other materials which have this property, like other stoichiometries of vanadium oxides or some other titanium oxides, etc. But this change of properties is not only static conductivity, which is what this graph shows, but this translates also to terahertz conductivity, gigahertz and terahertz conductivity, and it also translates to optical and infrared range of wavelengths. So here are the data from experimental data from describing real Vo2 film and its dielectric function. And here you can see that at room temperature, this is a dielectric which has quite high index of refraction, quite high dielectric constant. There are some non-negligible losses. And as you increase the temperature past these 70 or 68 degrees, you go to higher temperatures, the phase transition happens, and you will get negative dielectric function, which is related to metallic behavior and high reflectance of light from such material. And this change is really significant, one of the highest in nature in this region, and therefore that's the main reason why Vo2 is so popular and so often used in tunable metasurfaces. There are basically two means how you can incorporate any tunable material into metasurface. You can either use it as a tunable substrate. That is probably the most straightforward way. So you nanostructure your metal or dielectric as you are used to do in conventional metasurfaces, and you use some phase changing substrate, either Vo2 or GST or some other. And by this approach, you can somehow use your knowledge of nanostructuring, for example, metals, like in this case, or you will use more advanced approach and you will try to nanostructure the Vo2 or the GST itself. And again, there have been some works doing this, and me and my colleagues were also somehow involved in this in this, as I will mention in a minute. This all started in 2015 when I was an Erasmus student in Stefan Meyer's group, and with Daniel Ley we were investigating how actually this tunable substrate, this Vo2 thin film under gold nanoparticles, gold nanodiscs, how it influences the plasmonic resonance of these gold nanoparticles. And we get quite nice results that by tuning the temperature from 30 to 80 degrees across the phase transition, you are able to tune the plasmonic resonance. Here is extinction intensity, which is proportional to the amount of scattering and absorption happening in the gold nanoparticles. How this plasmonic resonance shifts to short wavelengths because the VO2 underneath undergoes the characteristic phase transition. And here is a plot showing the resonance wavelength extracted from these experimental data as a function of temperature. And here you see the typical hysteresis that is characteristic for many phase change materials actually, or for other phase changes, not only the structural ones, where you see that you need to decrease the temperature slightly more, and you have some in order to get VO2 back to its original state. And the width of this hysteresis tells you something about the quality of your film and about mono or polycrystallinity of your VO2. What we also did in this paper was that we investigated how by UV illumination, by UV light pulses, you can push the VO2 through the phase transition while keeping the external temperature same. And this is also related to the volatility of VO2 phase transition. So here you see how the resonance wavelength can be pushed to the blue side while when you illuminate it with UV light pulses of different lengths or different powers. And maybe let me start the laser pointer. And if you basically latch the VO2 at temperatures close to its phase transition, even the small energy carried by the UV light can push your material through phase transition. And what is nice, that this phase transition or this transition is then non-volatile. So unless you decrease the temperature below, the VO2 stays or is latched in this half transition state and keeps like that even when you stop the UV illumination. So it's not totally non-volatile because you still need to keep the temperature above room temperature, but if you use UV light, you can basically for quite a long time keep the VO2 shifted, which is a nice nice feature, I would say. Then what we did was a collaboration with group of Richard Haglund from the United States. And they were capable of fabricating really nice thin films of VO2. And what they observed was that based on a different cut of their sapphire substrate, because this is a sapphire crystal, and you can cut it in different planes, which are traditionally denoted as C, A, M, or R. If you deposit if you deposit your VO2, for example, in A-cut sapphire, you will get these nice beams of VO2 or nanobeams of VO2, unlike the conventional case where you have this typically polycrystalline VO2 thin film. And when we realized there is a confinement in these nanobeams, we thought, okay, this might also exhibit plasmonic resonance, because plasmonic resonance is always related to some sort of confinement or localized plasmonic resonance is related to confinement of your material. So we investigated these films a little bit more. We did AFM, we did XRD on them. We studied the orientations and described how the orientation of the sapphire substrate gets translated into these into orientation of the nanobeams as well. What is the mechanism behind? And most importantly, we studied the optical properties of these materials. And of course, as this material is anisotropic, it will be polarization sensitive. And this is exactly what you see on this graph. So again, we measured extinction by combining various detectors and light sources in FTIR microscope and spectrometer. And you see that at room temperature, there is basically very weak dependence on polarization, that is solid line and dashed line. And polarization is denoted by these arrows. So in the visible range, there is some non-negligible anisotropy in your films. At near IR and mid IR, the anisotropy gets lost. But as you push your VO2 into its metallic state by heating it up, you can get very nice localized plasmonic resonance in the transverse direction, so when your polarization is across the beams, and also you get some sort of longitudinal plasmonic resonance at very large wavelengths in the mid IR. So and it was basically fortunate for us that the region of the highest change or highest tunable window was in the region across the quite important telecom bands, where a lot of optical communication is done. And the extinction ratio, that means the metric how the extinction changes, was also quite significant. Last thing I would like to mention is our very recent work, which was done by our talented student Petr Kepic, who in collaboration with Hauran Ren, who was mentioned many times in Stefan Mayer's talk, they investigated this nanostructured Vo2. So we are moving from the continuous film and continuous substrate underneath nanostructures across some sort of hybrid self-assembled Vo2 nanobeam material or metasurface into really artificially nanostructured Vo2 film. So we investigated metasurface building blocks made of Vo2, which is nanostructured into a form of nanodisk. And here you can see calculated scattering cross-sections. So this is a very important metric for metasurfaces, because you want large scattering cross-section in order to influence the light which hits your metasurface. And we studied first theoretically and then also experimentally how these resonances, which are conventionally, and they were very well known from near infrared region, how they behave in the visible region. And here you can see that in the near and mid IR, in room temperature state, there is virtually no resonance of the VO2. Yeah, so the VO2 behaves like a metal here. Like a metal here, and it exhibits plasmonic resonance at these frequencies, which is tunable as you tune the diameter of your disk. This is very well known and expected behavior. And at room temperature in the dielectric phase, there is no plasmonic resonance at all. However, as you go to short wavelengths, you observe different behavior. The VO2 here is again dielectric function of VO2, and the stuff I was talking about a couple of slides ago, that in the near and mid IR, the VO2 undergoes this transition from dielectric, that is positive dielectric function, into a metal, so negative dielectric function. However, at visible range, and this was of course very well known, but not many people have used this property. At visible range, your dielectric constant stays positive all the time, no matter which VO2 state you are talking about. Of course, there is some change in the refractive index. There is virtually no change in loss, which is this imaginary part of the dielectric function. And this is exactly what we are using here in our work. So here in the metallic, so to say, state, which is kind of a misnomer in this context, because as you see, VO2 is no longer behaves like a metal at these frequencies or these wavelengths. You observe mere resonances, that is dielectric resonances of bound electrons and their currents in the nanodisk, which we ascribe to electric dipole and electric quadrupole mixture. And at room temperature, you again have higher, you have still positive dielectric constant, and you have these two modes now slightly separated or a little bit more separated, and you can, at least for large disks, you can see both of these modes separated. And of course, this was a simulation based on just this dielectric function, but Peter spent a lot of time optimizing the depositions and nanostructuring of these of this material, and he was able to achieve quite nice arrays of Vo2 nanodisks or nanocones, as you can see from this AFM image, and we then measure their extinction, that is related to scattering, of course, and we indeed observe that if you switch Vo2 from room temperature to high temperature phase, you observe quite significant change in the optical properties. And by in order to somehow evaluate this switching behavior or tunable behavior, we introduced a extinction modulation depth, that is some sort of metric or figure of merit that tells you how large the difference between the two states is in terms of quantity in decibels. And you can see that based on the size of your disk, you can of course achieve quite nice modulation depths across the whole visible and near IR range. We also studied how placing the Vo2 nanodisks into an array influences this behavior. So we did studies did experiments both on single nanostructures and on arrays of nanostructures, because they of course influence each other. You can have some lattice modes, etc. But I will skip it here, and I would like to mention also the last experiment of the paper, which is the demonstration of optical tunability. So similarly to the previous work with UV light, here we took an array of nanodisks, and here you can see its extinction. So here you can see this characteristic behavior, how you go in the visible range from one sort of dielectric mere resonance into another form of dielectric resonance, and we excited our nanodisks by a visible light laser. So by red laser, we illuminated our sample, and we measured extinction at higher wavelength. So we looked at the region where the change is is supposed to be highest, and influence it by visible light. So we were able, by visible light, tune the visible red transmission through our material. Here it is still at using external temperature. So this is basically a cross section of extinction at this measured wavelength. So again, here we can see this characteristic hysteresis behavior, but now it is caused by nanostructured Vo2 itself. Also, the resonance, of course, shifts from right to left. And here you can see how by increasing the laser power and exciting our Vo2 nanodisks locally by external laser, we were able to tune its transmission at visible wavelengths, which again I think is a promising feature for future work. So let me sum my presentation up. So I try to give you an overview of various possible means of introducing tunability into metasurfaces. I described Vo2 in detail, and I hope I mentioned its nice features and also its features which make your life complicated. And finally, I showed you the stuff we did with this interesting material. That is, first using it as a tunable substrate, then using it as a self-assembled metasurface itself, and then finally nanostructuring this metasurface by e-beam lithography and ion etching. So that's all from my side, and I'm looking forward to your question. Of course, yeah, sorry, I forgot to acknowledge all the people who work on this. So of course, Peter did a lot of work, especially with the most recent paper, but there are others who helped and contributed. Of course, Professor Tomáš Sikora, who was leading and mentoring the whole group. And here are other people from other universities who collaborated on this topic. So Stefan Meyer is here, Hauran is here, and of course. Okay, so that's all from my side, and thank you.
So maybe I will take over. So thank you very much, Filip. A nice talk. And questions, time for questions. So I will start once again. Maybe, yeah, please, you have mentioned that hysteresis. Can you make some comment on, let's say, on the quality of the films and benefits if you go for epitaxial growth? Does it have a sense or not? And yeah, something like that, the substrates and
okay. So of course, if you go towards epitaxial growth and you obtain high quality structures, which is not at all an easy task, you can get to very low hysteresis width on the order of units of degrees of Celsius, so like 2, 3, 4, 5 degrees of Celsius of the hysteresis width. And you can't go much below that because of the way how this phase transition happens in the VO2, and there are quite nice SNOM studies on single crystalline nanostructures from VO2. So basically the limit, short answer is that the limit is on the order of 3 to 5 degrees of Celsius.
Okay. So thank you very much. Some question?
Okay, can you hear me?
Yeah.
Perfect. So let me ask the following question. There's a lattice change there in the phase transformation. Does it impose any problem for you? Like, is there a finite number of cycles that you can go through? Is there any lattice elastic strain induced or something like that?
Yeah, thank you. So of course it can be a problem. The change in lattice parameters is very subtle. Yeah, as you can see in this scheme, yeah, the motion of the atoms is really subtle. So compared to GST, for example, it's not such a big deal that this changes. Of course, there is some sort of volume expansion or related to this, but it doesn't seem to have a really strong impact on the repeatability and endurance of your material. So there are papers who report millions of switching cycles with no observable change in the properties. So it seems to be. I don't say that GST is really bad in this. It also can sustain a lot of cycles, but in my opinion, it seems to me that VO2 is slightly better in this because the change is so subtle, and unlike the GST, which goes from crystalline to amorphous state, here it's really just a subtle motion of vanadium atoms.
Thank you.
So any other question, please?
Well, I might have the other one, and
okay.
now it is related to the.
Please raise your voice.
Yeah. So now it is related to the rate of the phase change. I saw that you showed something like tenths of seconds. So what's the best possible rate you can imagine for this phase change to happen?
Well, this time you mentioned is really related to our UV switching setup, where we used conventional UV lamp, nothing fancy. There are papers, and in principle, you are able to switch or drive the VO2 through its through this phase transition at ultra fast in ultra fast regime on the order of picoseconds. Of course, then there is then we can discuss whether it's really a structural change which is happening, or it is just an electronic effect related to excitation of your carriers and also on photons. Christian Apavu, who I mentioned at the end, and who is a co-author of several our papers, he has a nice paper describing this ultra fast changes of VO2. So in principle, you can go to picosecond regime, but of course not with the setup I showed with respect to the UV excitation.